Hello everyone, welcome back to our channel where we dive into the greatest minds and their groundbreaking discoveries. Today we're focusing on none other than the genius himself, Albert Einstein. Stick around as we count down his top 10 discoveries that have reshaped our understanding of the universe. And before we jump in, don't forget to hit that subscribe button and ring the bell so you don't miss out on our future videos. Number 10. Photoelectric Effect. Albert Einstein's discovery of the photoelectric effect fundamentally transformed our understanding of how light interacts with matter. Awarded the Nobel Prize in Physics for this revelation, Einstein proposed that light is not merely a wave, but also behaves like particles. These particles, or photons, carry energy that is proportional to the frequency of light. This insight was crucial because it explained why light could eject electrons from a metal surface, a phenomenon that was observed but not understood within the framework of classical physics. According to Einstein, when light of a certain frequency strikes a metal, the energy from the photons is absorbed by the electrons. If this energy surpasses a specific threshold, it frees the electrons from the metal, creating what we know as the photoelectric effect. This groundbreaking idea led to the quantum revolution in physics and has applications in technologies such as solar cells and photodetectors, which are integral to modern electronic devices. Number 9. Brownian Motion. Albert Einstein's exploration of Brownian motion in 1905 provided concrete evidence for the existence of atoms and molecules, previously a contentious topic among scientists. By analyzing the random, jittery movement of pollen particles suspended in water, Einstein offered a mathematical explanation, asserting that this motion resulted from countless collisions with much smaller, invisible water molecules. This insight bridged the gap between observable phenomena and atomic theory, offering a quantitative method to estimate Avogadro's number and the size of molecules. Einstein's work on Brownian motion not only supported the molecular hypothesis, but also laid foundational principles for statistical physics, profoundly impacting how scientists understood the underlying structure of matter. Number 8. The Special Theory of Relativity. Albert Einstein's Special Theory of Relativity, formulated in 1905, revolutionized the field of physics by introducing a new framework for all of physics and proposing new concepts of space and time. He postulated that the laws of physics are the same for all non-accelerating observers, and he showed that the speed of light within a vacuum is the same no matter the speed at which an observer travels. This theory emerged from Einstein's analysis of the interrelation between space and time and led to the famous equation E equals mc squared, expressing the equivalence of mass and energy. Number 7. E equals mc squared. Perhaps Albert Einstein's most renowned contribution to the world of physics is the equation E equals mc squared, a direct outcome from his special theory of relativity. This simple yet profound equation encapsulates the idea that mass and energy are interchangeable, unveiling a fundamental principle of the universe. E equals mc squared means that energy E equals mass m multiplied by the speed of light c squared. This relationship showed that even a small amount of mass could be converted into a tremendous amount of energy, as demonstrated in the energy released in nuclear reactions. This discovery has not only deepened our understanding of how the universe operates, but also laid the groundwork for various modern technologies, including nuclear power and medical imaging techniques like PET scans. Number 6. General Theory of Relativity. Building on the foundations of his Special Theory of Relativity, Albert Einstein introduced the General Theory of Relativity in 1915, a revolutionary theory that redefined how we understand gravitational phenomena. This theory posits that gravity is not a force as Newtonian physics had previously suggested, but rather a curvature in the fabric of space-time caused by mass and energy. According to Einstein, massive objects like planets and stars warp the space around them, and other objects move along these curves, which is perceived as gravitational pull. This new perspective on gravity has been confirmed by numerous experiments and observations, such as the bending of light by gravity and the precise orbit of planets. Einstein's general theory of relativity has not only expanded our comprehension of the cosmos, including black holes and the expansion of the universe, but it has also become a crucial tool in technologies that require precise measurements of time and space, like GPS satellites. Number 5. Einstein's cosmological constant. Albert Einstein introduced the cosmological constant, denoted as lambda, in his field equations of general relativity in 1917 to account for a universe that was static and balanced. At the time, the prevailing belief was that the universe neither expanded nor contracted. The cosmological constant was a term he added to allow for a static universe without gravitational collapse. However, after Edwin Hubble's observations in 1929 confirmed that the universe was indeed expanding, Einstein reputedly referred to the cosmological constant as his biggest blunder. Number 4. Bose-Einstein condensate. In the 1920s, Albert Einstein expanded on Satyendra Nath Bose's work on the quantum statistics of photons, which led to the prediction of the Bose-Einstein condensate, BEC. This state of matter occurs at extremely low temperatures, where a large number of atoms occupy the same quantum state, essentially behaving as a single quantum entity. The Bose-Einstein condensate represents a state where particles move in unison and exhibit macroscopic quantum phenomena such as superfluidity and superconductivity. Number 3. The equivalence principle. A cornerstone of Einstein's general theory of relativity, the equivalence principle is an elegant concept that posits that the effects of gravity are indistinguishable from certain aspects of acceleration and motion. This principle led Einstein to conclude that gravity could be described as the curvature of space-time itself. The principle has profound implications, particularly in astrophysics, as it predicts that light will bend in a gravitational field, a phenomenon later confirmed during solar eclipses. The equivalence principle is crucial for understanding modern physics, including the behavior of objects in gravitational fields and the workings of GPS technology. Number 2. Laser theory. Albert Einstein laid the theoretical foundations for the laser in 1917 with his paper on the quantum theory of radiation, which described the process of stimulated emission. This theory posited that electrons in an excited energy state could be induced to emit light of a particular wavelength when they return to a lower energy state. Number 1. Unified field theory. Albert Einstein spent the latter part of his career attempting to develop a unified field theory, which aimed to describe all fundamental forces and the relationships between elementary particles in one single framework. Although he never succeeded in completing this theory, his relentless pursuit significantly influenced the development of theoretical physics. Einstein sought to extend the general theory of relativity to include electromagnetism in a way that merged the gravitational and electromagnetic fields into one mathematical structure. This quest laid the groundwork for later theories of force unification, inspiring future generations of physicists. Thanks for watching. If you enjoyed this video, give it a thumbs up and don't forget to subscribe for more amazing content. Until next time, keep questioning and keep exploring.